Okay guys, we're on lesson 13. Of course, this is Saxon Algebra 2. And again, lesson 13, talking about substitution and the area of an isosceles triangle. Just a couple things before we get into the actual working. We're dealing with substitution. Now, there's kind of an important rule called the substitution axiom. The substitution axiom, you can see it on page 71 of your book, and it's broken down into three main parts. It says changing the numeral by which a number is named is an expression, an expression does not change the value of the expression. And so we can change the numeral, like it says, with a number as its name doesn't really change the value as long as we're replacing it with the same thing, or an expression that means the same thing. It's not going to change the value. For instance, we could say 4 equals 2 plus 2. 4 and 2 plus 2, they mean the same thing. We could replace those in that equation and not hurt anything. For any number a and b, if a equals b, then a and b may be substituted for each other. And so we have two different numbers or two different ideas, and they could be equal to each other. We can substitute. And if a equals b, and then a may replace b, or b may replace a in any statement without changing the truth or falsity of that statement. So they all kind of mean very, very similar things, those three basic points. But you can see the substitution axiom on page 71, lesson 13, if you want to go over that. So go ahead and flip the page. You'll see on page 72 if you're looking there. And we're going to talk about how to use that substitution axiom with some basic equations here, systems of equation. Now you see, of course, system of equation, we have a couple different equations. They're connected. What all this simply means, breaking it down, is that the x in this equation is going to be the same as the x in this equation. Well, the y in this equation is going to be the same as the y in this equation. So when you see those braces there, that's exactly what that means. Okay, so how do we solve for x and for y using substitution? Now we know what substitution is. Again, it's putting something in place of another thing. And when I hear substitution, I automatically think of a basketball game and a coach putting in somebody for somebody else. Okay, this guy is going to substitute for another guy. He's going in, the other guy's coming out. That's what we're going to do with these equations. We're going to put one thing in for another. And remember that substitution axiom said that if we have a system or a solution that we can plug in for a specific number, it's the same thing. It doesn't hurt it. So remember, if I have the number 4, but I have the solution 2 plus 2, I can replace those one with another without hurting the equation. So we're going to do that right here. And when I look at these two equations, I can automatically see something. I can see that x equals y plus 5. And then automatically I can think, okay, I can substitute y plus 5 for x. Well, it already says x equals y plus 5, so where do I substitute that? Remember, this x is the same thing as this x. So what I want to do is I'm going to take that y plus 5 and substitute it for everywhere I see this x. So I want to step over here and rewrite this so we can see it. Now, instead of saying 3x, it's going to say 3 times y plus 5 plus 2y equals 5. Say, why does it say that? Well, it says that because x is equal to y plus 5, and if x is equal to y plus 5, I can put that y plus 5 here. So now it comes down to the question, why do we even do that? Well, because instead of having an x and a y in this equation, now I have just y's. And with one variable, I can solve for that variable. Can't do that with two variables. Have to get it down to 1. All right, so we'll go ahead and multiply this out. We'll have 3y plus 15 plus 2y equals 5. All right, and so now once we get to this point, combine like terms. I have 5y plus 15 equals 5. Remember, my whole goal is to get the y's on one side by itself, what I'm looking for, everything else on the other. So I'm going to change sides, change signs. This 15 becomes a negative 15 on this side. 5y equals negative 10. 5 minus 15, negative 10. Divided by 5 on both sides. I get a negative 2. So now I know that y equals negative 2. Still need to solve for x. How do I solve for x? That's the easy one. I'm just going to plug what I know y to be into this equation, because x equals y plus 5, or x equals negative 2 plus 5. So x is negative 2 plus 5, or just 5 minus 2, and gives us 3. Does that make sense? Hopefully it does. We'll give a couple more problems here that are basically the same thing, but 13.2 is going to require us to do a little more work, and we'll see what we mean. So we have 3x minus y equals 11. We have 2x plus 3y equals negative 11. Now, we don't have anything like we had up here. It says x equals something or y equals something, so we're going to have to work that out in one of these equations. The obvious one to use, at least in my opinion, what I'm thinking, is going to be the first equation. And why is that? Well, because this has a 3x, a 2x, a 3y, but this is just a y. So we can rearrange that equation to make it say y equals something. And we're going to go ahead and do that. What I'm going to do is I'm going to take this negative y to the other side over here, and then I'm going to take this positive 11 to this side over here, because my whole goal is to get y by itself, to say y equals something. So what we end up with is 3x. When I bring this 11 over, it's a positive 11 on this side, bring it to this side, it becomes a negative 11, equals my negative y here, take it to the other side, becomes a positive y. So now I have y equals 3x minus 11. Now I can take that and plug it into my equation here. So 2x plus 3, not y, but 3x minus 11 equals negative 11. I'm going to go ahead and multiply using my distributive property right here. 2x plus 9x. Let me throw that in there, but I don't want to miss that. Plus 9x minus 33 equals negative 11. Combine my like terms. 2 plus 9 is 11x. I have this negative 33. What do I do? Do you remember what our saying is? Change sides, change signs. So 11x becomes or equals 22. Divide by 11 on both sides, and I'll find out that x equals 2. I'll go ahead and plug that right there. All right, now that I know that x equals 2, all I'm going to do is take that 2, plug it into my equation for y. So 3 times 2 minus 11 equals y. 3 times 2 is 6 minus 11 equals y. 6 minus 11 is negative 5. And so y equals negative 5. Hopefully that makes a little sense. Down here, 13.3, you can also see this in your book. It's going to be much the same thing. But I have an x plus y equals 20. So what in the world do I do there? We're going to do the same thing we did right here. We're going to say, and I'm just picking x right now, so I'm going to say x equals, I'm going to take this positive y, remember, change sides, change signs, and you could use y, you could say y equals 20 minus x, but we're going to say x equals 20 minus y. It's going to be the same. You can work the same way. One way you'll just be solving for y first, this way, and then if you said y equals 20 minus x, if you used this one, you'll just be solving for x first. So it doesn't really matter which way you go. There's no hard, fast rule. I just picked one and went with it. You see what the book does. Maybe we should go with the one the book goes with. They go with x equals 20 minus y, which is the first one I wrote. So we're going to plug 20 minus y into our other equation. So 5 times 20 minus y plus 10y equals 150. Using distributive property, go ahead and multiply here. 100 minus 5y plus 10y equals 150. Getting y's on one side by itself, everything else on the other. We're going to combine the y's here. I have a 5y. Now I have 100 here. Change sides, change signs. So 150 minus 100 equals 50. Divide by 5, both sides here. I'll see that y equals, I know it's going downhill, but the way I'm writing, y equals 10. Okay. So if y equals 10, what is x going to be? Well, remember, x is 20 minus y, or 20 minus 10. So x equals 10 as well. That's pretty simple. Let me point this out too. I think the book gives our answers in ordered pairs. So this ordered pair would be 3 and negative 2. You know, and I didn't even check these with the book, so hopefully this is right. I think it is 2 and negative 5, and 10 and 10. Okay, so if there's any questions about using this system of equations and solving for x and y with substitution, let me know. It's a pretty simple process. I know sometimes with this one and this one, it may get a little difficult right at first, knowing how to substitute, but in these cases, just get an x or a y by itself, and then substitute whatever's on the other side of the equation into the next equation. That kind of simplified. All right, we're also looking at 13b, the area of an isosceles triangle. Now, when we say that, I've got to give some definitions out here. What is an isosceles triangle? An isosceles triangle is a triangle that has two sides that are the same length, and most often looks like this. Okay, so we see this triangle, and they want us to find the area. Now, we think automatically that should be easy, because the area of a triangle is just the base times the height, and then divided by 2, because it's a triangle, remember? So we know the area of a triangle is equal to base times its height and divide by 2. Basic formula that we've already come across. But we're put in a position to find the area of an isosceles triangle without having the height. You say, well, Brother Chad, we have the height. It's 5. No, that is the slant height. And you kind of need to remember that just because it's going up doesn't make it the height. In order for it to be the height, it has to be a 90-degree angle, showing that height there. You say, does it really make that much of a difference? Yes, the actual height is going to be less than the slant height. You can maybe think if you had a room, you had a floor and the ceiling, and you had, well, maybe an 8-foot ceiling, that's kind of normal. And let's say you had a 10-foot board. Could you take that 10-foot board, if it's laying horizontal flat, and then tilt it up and pick it up and stand it straight up in that 8-foot room? No, you couldn't. That board would still be 10 feet, but it'd be at an angle. That would be the slant height of a triangle, that 10-foot, where the actual height would still just be 8 foot. So we understand the slant heights are always going to be a little bigger. I say a little bigger. Sometimes they can be a lot bigger than the actual height. So we got to make sure not to confuse the slant height with the actual height. So that being said, how do we find the actual height? I'm glad you asked. We're going to go back to just a couple lessons ago, our Pythagorean theorem. Okay, so what I did right here is I just broke this triangle in 2 pieces. I cut it right up the middle, spread it a little bit, and made 2 pieces out of it. So I have a 2 here and a 5, a 2 and a 5, and I need to solve for this side right here. This side right here is going to be my height. How do I do that? Well, remember that a squared plus b squared equals c squared. That's our Pythagorean theorem. Now, what is a, what is b, what is c? A and b don't matter. It doesn't matter whether you use this and this. C is the only one that matters. C is always the hypotenuse, always the longest side of any triangle, of any right triangle. This is the hypotenuse. So a squared plus 2 squared is going to be equal to 5 squared. And so we're going to say we're looking for a right here. Our book may tell us something different. That's okay. They're using a slightly different formula, not a problem. We have a squared plus 4 equals 25. Okay, so where do we go from there? Well, get a squared by itself. A squared equals, change sides, change signs. 25 minus 4 is 21. Now, is that our answer? No, it's not, because we're not looking for a squared, we're looking for a. So how do we get a? Well, we got to square root this side, but what we do to one side, we have to do to the other, because it's an equation. It's equal on both sides. So now we can say a equals the square root of, and that's kind of ugly, but the square root of 21. So what is our height? Well, it's the square root of 21 here, so that makes it right here. Just rewrite it again up here. Square root of 21. Now that we have the height, can we find the area of the isosceles triangle? Absolutely. Go back to our formula. Base times height divided by 2. What's our base? Well, our base is 4. Times what's our height? Square root of 21. And what does our formula tell us to do? Divide that by 2. All right, so we can make it pretty simple here. We're dividing by 2. Let's cancel right there. And so we can now say 2 in the square root of 21, because we just multiplied 2 times square root of 21. And our units are in centimeters. So it's going to be centimeters squared, because we always have a square unit when we're dealing with area. All right, so it's very, very simple. I do want to point out real quick in your book, if you're trying to follow along in your book with this right here, you're going to notice that they use 5 squared equals h squared plus 2 squared. The h squared will be the same thing as our a squared. I don't want you to get confused with that. They use the Pythagorean theorem. They just made it h for height, so you can understand what they're looking for. Again, if you have any questions, let me know, and we look forward to seeing you next class.